Hi everyone. Today, we're going to explore two of the most important concepts in machine learning: supervised learning and unsupervised learning. What's the difference between the two? When do we use one over the other? And how do they actually work? Stick around. We'll break it all down step by step, with clear explanations and simple examples. Let's start by looking at a basic table to understand the difference. On the left, we have supervised learning. Here, you can see that we have multiple input features, labeled as X, X2, X3, all the way to X. But notice something important. We also have a column labeled Y, highlighted in pink. That's the target, the correct answer. We're showing the model both the inputs and what the output should be. That's why it's called supervised, because the model is learning from examples that include the right answer. Now look at the right side. Unsupervised learning. It has the same input features, but one big difference. There's no Y column. There's no label or correct answer to learn from. In unsupervised learning, the model has to figure things out on its own, like finding patterns, clusters, or structures in the data without any guidance. That's the key difference. Supervised learning uses labeled data. Unsupervised learning doesn't. Now that we know what supervised learning is, let's break it down a bit further. Supervised learning is typically divided into two main types: regression and classification. We'll start with regression. If the target variable Y contains numeric values, like house prices, temperatures, or sales figures, then we're working on a regression problem. That means the model is learning to predict a continuous number. Some common examples of regression tasks include predicting the price of a house, forecasting product sales, estimating stock prices. So remember, if the output is a number, it's regression. Now let's look at the second type of supervised learning, and that is classification. In classification, the target variable Y contains categories or labels, rather than numbers. So instead of predicting how much, we're predicting which class, which group, or which label something belongs to. For example, the Y column might contain labels like spam or not spam, cat or dog, or even medical results like disease present or no disease. These are some of the most common classification tasks: email spam detection, medical image classification, sentiment analysis, classifying text as positive, negative, or neutral. Now that we've seen what regression and classification are, let's wrap up the topic of supervised learning with a look at some of the most commonly used algorithms. We'll break them down into three categories: algorithms for regression only, algorithms for classification only, and those that can handle both. For regression, we often use linear regression, one of the simplest and most widely used models, and ridge or lasso regression, which add regularization to reduce overfitting. For classification, we commonly use logistic regression, especially for binary classification tasks, and naive Bayes, which works well for text and probabilistic problems. But many algorithms are flexible and can be used for both regression and classification, depending on how you set them up. These include decision trees, random forests, XGBoost, and light GBM, powerful ensemble models, K-nearest neighbors, KNN, support vector machines, SVM, and neural networks, especially in deep learning applications. Each of these algorithms has its own strengths and use cases, and in practice, it's common to try multiple models and compare their performance. This brings us to the end of our supervised learning section. Next, we'll explore unsupervised learning. Now, let's move on to the second major type of machine learning: unsupervised learning. Here's the most important difference from supervised learning. In unsupervised learning, there is no target variable. There's no Y column, no label or correct answer to learn from. We only have the input features, the X values, and the model's job is to find hidden patterns, groupings, or structure on its own. Let's take a look at some of the most common unsupervised learning tasks and the algorithms used to solve them. Clustering, grouping similar data points together. Examples include k-means clustering, hierarchical clustering, DISCAN, Gaussian mixture models, GMM. Anomaly detection, identifying data points that don't follow the normal pattern. A common method here is autoencoders, especially for detecting outliers in complex datasets. Dimensionality reduction, reducing the number of features while preserving important information. Popular methods are PCA, or Principal Component Analysis, TSNE, which is great for visualizing high-dimensional data. Association rule learning, finding relationships between items, like in market basket analysis. Common algorithms, a priori algorithm, FP growth. Let's begin with one of the most well-known unsupervised learning tasks, clustering. In clustering, the model groups similar data points together based on patterns it finds in the input features. And remember, we're doing this without any labels. The model figures it out by itself. Some of the most common clustering algorithms include k-means clustering, hierarchical clustering, Discan, and Gaussian mixture models, GMM. So where is clustering used? Here are some real-world applications. Customer segmentation, grouping people based on their behavior or preferences. Document or text clustering, organizing similar articles or search results automatically. Clustering helps us discover structure in unlabeled data, making it incredibly useful for marketing, recommendations, and content organization. Next, we have anomaly detection, another powerful use case of unsupervised learning. Anomaly detection is all about finding things that don't fit, unusual patterns, or rare events that stand out from the norm. This is especially important when the anomalies are dangerous, fraudulent, or costly. A common algorithm used here is the autoencoder, a neural network that reconstructs the input and flags anything that doesn't match well. Common anomaly detection tasks include fraud detection, catching suspicious credit card transactions, fault detection in manufacturing, identifying defective products, medical anomaly detection, like spotting abnormal heart rhythms from ECG data. Unsupervised anomaly detection is critical when we don't have labeled examples of what's wrong. The model learns what's normal and flags the rest. Now let's look at dimensionality reduction, another key task in unsupervised learning. This is all about simplifying the data by reducing the number of features without losing too much information. Dimensionality reduction helps us make sense of complex, high-dimensional datasets. Chart-decreasing common algorithms for this task include PCA, or Principal Component Analysis, TSNE, which is especially useful for data visualization. You'll often use dimensionality reduction for data visualization, projecting data into 2D or 3D to spot clusters. Noise reduction, removing irrelevant or redundant features. Pre-processing, simplifying data before feeding it into a model. This is a powerful tool for working with text, images, and large datasets where interpretability and speed matter. Finally, let's talk about association rule learning. Unlike other tasks, this one looks at relationships between items, especially what tends to occur together. Think of it as answering the question, if a customer buys A and B, what else are they likely to buy? Common algorithms include a priori algorithm, FP growth. Typical use cases include market basket analysis, understanding buying patterns in retail, product recommendation, suggesting items that are frequently bought together. This is the kind of logic used behind many customers also bought sections on online stores. And that wraps up our introduction to supervised and unsupervised learning. We explored the key differences, common tasks, and popular algorithms used in real-world machine learning. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell for more beginner-friendly AI and data science content. Thanks for watching, and I'll see you in the next one.